Hello everyone, welcome to Astronomy 103. Today we're going to be talking about star formation and lifetimes. Okay, so the topic today is both how do stars form and how long do they live? So what we're going to do today is talk about what and why form stars. Why do stars form? How do they form? What's going on? Talk a little bit about the process of star formation and look at how this looks on an HR diagram. And also talk about timescales. How long does it take for a star to form, and how long do stars live once they form? So first we have to figure out where we find young stars, because almost anything stars do is much, much slower than human timescales. So what we have to do is find places where stars are forming, because we're not going to be able to find a star going from completely unformed to definitely a star in our lifetimes. Also, stars spend a relatively short portion of their life forming. Stars spend most of their life sitting on the main sequence, turning hydrogen into helium. So it's a good idea to find a bunch of stars all forming to study them rather than just looking at random stars and hoping we catch them when they're relatively young. Now, where do we find stars? We find them in nebulae. Now, nebula is a word that means cloud. Nebulae is the plural. And this is a word for all sorts of clouds of gas and dust in space. If it's a big cloud of gas and dust and it's in space, you call it a nebula. And stars form in a certain kind of nebula. So we call these places that we find star formation going on as molecular clouds. Molecular clouds are so named because they're clouds, they're nebula, and they are cool enough, and by cool enough I mean only about 10 to 20 Kelvin, that allows molecules to exist in these clouds. Most of the nebula in space, the atoms are kind of on their own. These clouds are cool enough that we get molecules, typically hydrogen, H2, so that's two hydrogen atoms sharing a chemical bond that makes them a hydrogen molecule, and carbon monoxide, CO. There's plenty of other trace molecules. In fact, there's whole fields of astrochemistry, people who study how molecules form in space. But H2 and CO are kind of the big ones. H2 just because it's hydrogen. Hydrogen is the most common element everywhere in space, with some very local exceptions. And CO because CO is really easy to see for if you're an astronomer. We're very good at finding CO, less good at finding H2. Now, one of the important things you can see in this picture, so this is a picture of a smaller molecular cloud, Barnard 68, and in visible light, all you see is black. The cloud is cool, so it's not glowing. It's not producing an emission spectrum. And there's nothing nearby to kind of illuminate it. But it's very good at absorbing light, and there's a lot more stuff in the way, relatively speaking. There's a lot more stuff in the way, blocking all the starlight. That's why we see it as kind of a black spot. But if we look in the infrared, the cloud is more transparent. So the right picture on the right is in the infrared. You can see the stars behind Barnard 68. Now, Barnard 68 does redden the light that goes through it. Even in the visible light picture, you can see that the stars near the edge of the cloud, their light is not completely absorbed. They still look reddened, kind of, making you imagine the cloud has kind of a reddish cast, even though it's mostly just black. That's actually the same process that makes our sun look reddened when it shines through our atmosphere. Makes the stars look reddened when they shine through a molecular cloud. So in general, a lot of studying star formation has to be done in the infrared, which may mean spacecraft or may mean certain things can be done from Earth. One of our nearest star formation regions is the Orion Nebula. If you go outside and look for the constellation of Orion, it's that hourglass. Below Orion's belt, there's a series of 3 stars, and the middle star is not a star, it is the Orion Nebula. You might notice it looks a little fuzzy. It's one of those big clouds of gas and dust. Some of that gas is too hot for star formation, but it's still it's giving us that lovely emission nebula. But other parts of the cloud are cool and dense enough to make stars. So we study the Orion Nebula in the infrared to both see through all the gas to see young stars being formed, and to study the cooler, denser molecular clouds parts of the nebula. Star formation regions contain enough material to make many, many stars. This is a bigger picture of Orion. You can see the hourglass, the shape of Orion, is drawn in blue lines over an infrared picture of Orion. And again, you can see the bright Orion Nebula kind of sitting below its belt. You can also notice there's a lot of bright gas of various temperatures hanging around Orion. Now, all of this looks really dense, but even the densest molecular clouds are much less dense than the air in your room. You know, it only looks dense because it's light years and light years of empty space. Even a very diffuse cloud will look like a lot when you look through a light year of it. So we have all these clouds. You know, all clouds are nebulous. Some of them are molecular clouds, and some of those molecular clouds are called giant molecular clouds because they're very big. So what makes them start forming stars? Now, when we were talking about the sun and we were talking about the structure of stars, we've mentioned that the sun is balanced by gravity trying to pull everything inward, and the thermal pressure of the gas trying to make everything go outward. This is true for a nebula too when it's not changing in size, or one of these molecular clouds. It's just that the gravity is much weaker, so you don't need as much thermal pressure. You don't need a star that is thousands or tens of thousands or hundreds of thousands or millions of degrees Kelvin to balance the gravity. You have a much more diffuse cloud, so you can balance it with a cloud that is 50 Kelvin, 100 Kelvin. But on the other hand, because that thermal pressure is so weak, it doesn't take much gravity to overbalance it and start the collapse. You don't need to get much gas in one place to do it. You just need to get a slight overdensity, a slight spot that's denser than the other. Gravity starts to win and the cloud starts to collapse. And this is hard to observe because it happens pretty slowly. So we also build computer simulations. Turns out gas is pretty straightforward to behave, and so we can model how stars form. Some of the pictures I'm going to show you are simulations rather than actual pictures. So, you know, you can tell the computer, okay, here's a cloud of hydrogen and helium and carbon monoxide and a few other things. You know, let's start with it evenly distributed and see what happens. And all kinds of things can trigger this collapse, can trigger that overdensity. Even just the light from nearby stars can push on this gas. It's really, really light. So nearby stars can sculpt it away or push it into new locations. Or if you want something a little more energetic, a supernova can clear out portions and it can push portions into other portions, which will make them denser and start to collapse. As we're going to talk about when we get to galaxies, large-scale effects in the Milky Way trigger waves of star formation. That's why we can see our spiral arms in some galaxies. Those are marked by the regions that are making lots of stars. And even just random motions. All these gas molecules are just kind of flying every which way with no particular pattern. And sometimes just by chance, you'll get a bunch in one place and kick off star formation, which can trigger some of these other effects, like the light from nearby stars or supernova. Once you get one star, you can start to make more. And stars do tend to form in groups and clusters. So what happens with our cloud is, you know, even if it starts out pretty even, one of those outside forces or internal forces will start it to collapse, and you get this complicated filament structure. Most of these molecular clouds, again, they've got enough stuff they can make dozens of stars. So as they collapse, the cloud starts to kind of fragment and clump up. So those individual clumps are going to form stars or multiple star systems, or binary stars or trinary stars. And so the whole cloud is not going to turn into one big star. It's going to turn into a bunch of little to big stars. It's going to turn into a whole bunch of stars. All right, so what happens is you get a big cloud, and we've talked a little bit about this when we talked about planet formation, is the gravity starts to compress the gas. Now, the cloud is still pretty dark. It's still pretty good at absorbing light. So the gas is going to heat up, which moderates the collapse. It can't happen as fast as what we call the free fall time. It can't just all fall in to the center. It is balanced by that thermal pressure, which is not enough to stop the collapse, but is enough to slow it. And again, like we talked about when we were talking about planet formation, a lot of the gas, most of the gas ends up in the center forming our protostar, our before star, our object that's going to be a star. And again, it might form one or two or several of those, depending on the size of the cloud. But as the cloud collapses, it spins faster and faster because of that conservation of angular momentum. And again, go back to the forming planets lecture. And we get a disk around the star, what's called a protoplanetary disk. Or sometimes a protoplanetary nebula, because again, that's our nice word for clouds of gas in space. Now the downside of this, well, the upside of this is we can tell that the star is going to form planets, which is pretty cool because we like planets. The downside is that this disk can block what's going on with the protostar. Can be hard to study the protostar when you have a protoplanetary disk in the way. There's lots of stuff still around the star, even as it collapses to start forming. So it's hard to study. So the whole thing is heating up as it falls into itself. Our protostar is climbing in temperature. So it's also starting to glow brighter and it's starting to look bluer and bluer. Now remember, it's starting pretty cold. So bluer and bluer still means infrared, just less infrared. You also start to develop the star's magnetic field. Our sun has a magnetic field and so do protostars. In fact, they have particularly strong ones. And this can steer out jets to come out of the poles of the protostar. Now the cool thing about this is that these are not shrouded by the protoplanetary disk. So we can actually see these. And we can identify, forming stars, embryonic stars, if you would, by where the jets are coming out. So here's some picture of some forming stars in Orion. You can see the scale bar. It's about 0.1 light years, which would be about 0.03 parsecs. This is still, 0.1 light years is still tens of thousands of astronomical units. So these are much, much bigger than our final solar system. These are showing some of the clumps as they collapse into these protoplanetary disk plus a protostar, and zoomed in deep into the Orion Nebula. And then here are some pictures of protostars with jets. I particularly like the bottom one, because you can see kind of the disk. You can see the jet coming out. And you can also see that the jet is changing. From 1995 to 2000, we see different structures. We can measure how fast stuff in the jet is moving. And again, we're working mostly in the infrared because if we try to look at the visible, we just get the mass of gas that is either too hot to form stars and is glowing, or is right temperature to form stars, so it's absorbing all the visible light. And one thing we look for is, as it's collapsing, it's gathering more and more mass to itself. And once it starts to kind of reach its final mass, it starts to be a little more visible. It's still probably got a bit of a disk. This isn't a sharp, sudden process. But we can start to see it as a star. And it's still technically a protostar. It still hasn't turned on yet. But since we can start to see this as a star, give it its own name. It starts to look more like a star than a little clump of gas. And we name it after the first one we kind of identified, which is T Tauri. So we call them T Tauri stars. Now, technically, it's still a protostar, but it starts to be easier to see in visible light. And this is a picture of the original T Tauri. You can see it's surrounded by all kinds of gas. So, all right, we're going from a protostar to a star. Now, for this object to become a star, it needs a bit more than 7.5 to 8% of the sun's mass. At that point, as it collapses, at some point, hydrogen fusion will start. It'll be putting out its own thermal energy rather than just gathering thermal energy as it collapses. It can start to basically come into equilibrium. It balances gravity pulling inward and the energy from fusion pushing outward. It settles onto the main sequence, and its light and stellar wind can start pushing out all the leftover gas, which we talked about with planet formation. So, all right, if the star is bigger than about 7.5 to 8% of the sun's mass, and that's a little variable depending on the star's composition, how much heavy stuff it has in it. You know, it settles on the main sequence and we have a main sequence star. What if it's smaller? Well, then we get those brown dwarfs. Those brown dwarfs are formed like stars, just like stars, except they don't have enough mass to start hydrogen fusion. So what happens is, a star contracts until it starts hydrogen fusion, and then it kind of settles into an equilibrium on the main sequence. A brown dwarf contracts until the atoms can't contract anymore. And that slows it down. It kind of settles into a final state, and then slowly continues contracting forever. Now, the pressure holding this thing up is not that equilibrium of thermal pressure and gravitational. It's an equilibrium between gravity and something called electron degeneracy pressure. We're going to come back to this because it's also important at the end of a star's life. This is a quantum mechanical force this is a quantum mechanical effect that limits how close electrons get to one another because they cannot be in the same place with the same energy level. Now, above about 100 to maybe 300 times the mass of the sun, at that point, the light and heat from this giant protostar will cause it to just fragment again, and we'll start to get more than one star. Even if it forms without collapsing, even if it gets to a protostar stage without fragmenting. Now we call this the Eddington limit. This is the limit where an object's own light and radiation will blast it apart. And this kind of sets the maximum size of stars. Now, now, just like with brown dwarfs, I'm giving you a range because it does depend a bit on composition. Stars that have more heavy elements, that's elements heavier than helium, have a smaller Eddington limit. They tend to interact more with their own light, so they only can grow to maybe a bit above 100 solar masses. A star that doesn't have very many heavy elements, it's almost pure hydrogen and helium, could grow to be maybe 300 or even more times the mass of the sun. It would be huge. Now, this is a picture on the side of one of the most massive stars ever known, Eta Carinae A. Or rather, this is a picture of Eta Carinae A and the stuff it's blasted out. It probably formed close to the Eddington limit, and it's been shedding mass all of its relatively short for a star life. So the nearby neighborhood is just shrouded in mass. And it is a binary star, and the other star is not a lightweight either, which makes determining its exact mass a bit tricky since the combined mass is quite large. So, all right, let's plot this on our HR diagram. That's how we organize our thoughts on stars. So a protostar starts out really, really cold, so it's very, very faint. And of course, since it's very, very cold, it's way off the right end of the diagram. As it collapses, it both heats up and it gets brighter. Remember, hot things tend to be brighter for a given size. So even though the cloud's shrinking, it's losing radius. The heating up as it contracts more than counters that. So it starts to get to star-like temperatures, an M star. And at that point, it's still contracting. It's going to contract until it gets to the main sequence, but the contraction is starting to counter the heating up. So it starts to get less luminous and settle out on the main sequence. Don't worry too much about the stages. Now, this varies a bit depending on how big the star is, the exact path. So we usually cut off the part here labeled 1. This is the cloud collapsing and forming our protostar. So around from 1 to 2 is around where we're definitely sure that is definitely a protostar. So now we're looking at stages kind of 2 through 4. for a bunch of different kinds of stars, from a 100 solar mass star to a 0.1 solar mass star. You can see the 100 solar mass star is going to be an O type, 0.1 solar mass star is going to be K or M. And the red line is our main sequence. In particular, it is the line where stars at age 0 sit on the main sequence, so it's the 0-age main sequence. Now we have to model this with computer models because it takes, even the big star takes thousands of years to form. And there is a little bit of a difference. Big stars tend to, by the time they are clearly protostars rather than clouds, they tend to have reached their final luminosity, and they just need to heat up and shrink to get to the main sequence, while a tiny star like a little red dwarf settles onto the main sequence by mostly just contracting until it gets to a stable place. Its luminosity is actually going down, but it's not heating up that much once it's clearly a protostar, because it's not very hot. The dotted line on this plot is just showing you where we can actually see the star clear the gas cloud. Now, the one more thing I want to comment on is the numbers on this plot. If you look along each of the lines of each of the tracks of how a star gets to the main sequence from its formation, you see a bunch of numbers. At top, you see 10 to the 2 to 10 to the 4. At the bottom with the tiny star, you see 10 to the 6 to 10 to the 8. Those are times in years, and each power of 10 is marked. So a 100 solar mass star, one of those big Eta Carinae type stars, only takes about 10,000 years to get to the main sequence from a big cloud of gas. It collapsed really fast because it's got a lot of mass, it's got a lot of gravity. That pokey 0.1 solar mass star, that's taking 10 to the 8 years. That's 100 million years rather than 10,000. It doesn't have very much mass, so its collapse is pretty slow. Now, another thing about stars is that in general, the smaller the star, the more of them we have. Whenever you're forming stars, you tend to form more of the small ones than the big ones. So for every one star between 10 and the maximum, you might get 200 stars that are between half a solar mass and the limit. So you might get 200 K and M types for every one O type. And you can notice this in our stellar neighborhood. We've got maybe 3 or 4 G types, a few more K types, an F type, that would be a Procyon, an A type, Sirius, and something like over 50 red dwarfs. And this pattern persists into brown dwarf sizes. There is some hint that as we get to smaller and smaller brown dwarfs, it eventually turns over and we start making very few of them, that eventually get to kind of a size where it's really hard to form such a small body. But we expect there are lots of brown dwarfs, and the only reason we don't find that many is because they're really faint and hard to see. Now, all right, so that's how you form a star. Eventually, what tends to happen is as you make stars in the same molecular cloud, they tend to scatter the gas a bit. Sometimes that's good because they're push gas together to make a new star, but they're also scattering it away from things. And eventually you make enough stars that all the gas, all the leftovers are kind of dispersed. It's not a terribly efficient process. So this is a picture of the Orion Nebula. And again, visible and infrared. The visible is better for seeing all the pretty colored gas. The infrared lets you see the stars, and it's forming, you can see that it's formed a bunch of stars. These 4 bright stars are called the trapezium. And you can see them in a telescope, and you can also see a bunch of other stars in the area. So what this ends up with is something we call an open cluster, a group of young stars that have probably all formed together, and they're still kind of clustered together. So for an older example of an open cluster, and this is another thing you can see, as you go outside, practicing good social distancing. But if you go outside to stargaze, you can see this. This is the Pleiades, the 7 sisters. This one's much older. It's more like, in fact, it's pretty old for an open cluster. It's more like maybe 100 million years old. And the gas in here, the diffuse kind of fuzzy stuff, is actually a coincidence. It's not remnants of the Pleiades forming. Now, what happens when you get a cluster is as the gas sheds away, cluster is less tightly held together by gravity, and you slowly lose stars to kind of just the ambient medium. Our sun is not in a cluster. It formed in a cluster. We call it the sun's birth cluster. But long, long ago, all the members kind of went their separate ways. So we don't know about any of the stars that our sun was born with. You can kind of see this happening. So near the Pleiades, there's another star cluster called the Hyades. And it's a lot harder to see, not because it's, tiny or faint. It's a lot harder to tell that's a star cluster rather than just a pretty star field. Now, the other thing we want to talk about, we say stars end their formation, they're stars rather than protostars when they get to the main sequence. And they mostly sit in one spot for their entire main sequence life. So they do have a little bit of change as they run through their fuel, but it's pretty unsubstantial compared to what comes before and what comes after. So what we can do is, we talked a little bit about this with binary stars, is the amount of mass in a star's core is proportional to its total mass. And the luminosity is telling you how much fusion is going on. How much light is the star producing depends on how much fusion it's doing, how fast it's running through its fuel. So we can calculate stellar lifetimes. And we can also check this by watching open clusters and seeing which stars in the main sequence leave the main sequence first. So what we observe is, just like massive stars are quicker to form, they're also quicker to leave the main sequence. An O-type star might only live 10 to the 7 years, that's 10 million years. A star like our sun would live 1,000 times longer. It would live about 10 billion years. And those little red dwarfs, well, they live forever. Well, not really forever, but something more like 1 trillion years. We can make theoretical predictions about what happens when a red dwarf runs out of fuel, but we've never seen it. There has not been enough time in the universe for a red dwarf to run out of fuel. Now, the interesting thing is, if you check those timescales, a red dwarf takes 100 million years to enter the main sequence from being a cloud of gas and dust. By that time, a big O star has not only entered the main sequence, but it's run through all its fuel and it's left the main sequence. So not only do stars live a long time, but the smallest stars live their lives really, really slow compared to the largest stars. So in summary, star formation kicks off when we have this molecular cloud that gets dense enough, by one of the reasons we discussed, that gravity overpowers the thermal pressure keeping it up, and it starts to collapse. The cloud collapses and fragments, and it forms a protostar as it heats up. The protostar starts out shrouded in the kind of remains of the cloud, or the nearby bits of the cloud, but it slowly either gathers all that up or starts to blow it away, forming our T Tauri star, and then ultimately, as it collapses, it starts fusing hydrogen and joins the main sequence. And when we're talking about timescales, big stars form faster than small stars, and big stars run through their fuel faster than small stars. So next time, natural question is, okay, we've talked about how stars are born, we've talked about how stars live, now it's time to talk about how stars die. So what happens when a star leaves the main sequence? I've talked a little bit about that by talking about the other kinds of stars on our HR diagram. I'll go into more detail.